Assalamualaikum dan salam sejahtera. Today we continue our discussion about the open channel, and today I would like to share with you a few equations that commonly used in open channel calculation. Previously, we discussed about the Reynolds number and also the Froude number. So in open channel, we use Reynolds number to determine whether it is laminar or turbulent, but you must make sure that you really understand how to calculate the Reynolds number, because we are not using diameter or length. We are using the hydraulic radius. So, and then you need to know how to determine your hydraulic radius from the cross-sectional area of your open channel conduit. And today, we will see how the flow calculation being done. Before that, I would like to give you two basic equation that can be used for this type of calculation. So the first one is the Chezy formula here. So Chezy formula is actually, it's reflect the same ideas of flow in pipe that we learned in fluid mechanics 1. It is telling us about the velocity of fluid that flow in the conduit, and then we calculate the velocity and so on. Okay, however, because in open channel we assume that there are no hydraulic pressure, so means that we assume the pressure is atmospheric pressure at all point in open channel. So means that from the Bernoulli equation, we have P over rho G plus V square over 2G and plus Z. It is mean that the terms of P over rho G can be neglected. So the only terms that occur in our calculation today is velocity and the value of Z. Okay, why the value of Z is still important? Because we know that in open channel, the water flow due to the gravitational force. So means that if your conduit is on the same level, means it's not inclined at certain angle, so mean the water will not flow. Okay, so let's say that we have something like this. So let's say we have a conduit, a drainage, for example, like this one. So we have point 1 here and point 2 here. So and then we have the length from point 1 to point 2 show as x equal to L, and then we have the angle here to make sure that water could flow from the left to the right side here, and then the Z is Y as shown in this figure. So and then to make it simple, so we could say that the tangent theta here, so we know that tangent theta is Y over L here, so we could say it is equal to S naught, to simplify our calculation later on. So and then if we do our Bernoulli equation, I think everybody here is familiar with Bernoulli equation. We use a lot of calculation using Bernoulli equation in fluid mechanics 1 and 2. So this is the P over rho G plus V square over 2G plus Z. So equal P over rho G P1 P2 plus V square 2G plus Z, and then plus total loss. Okay, so and then the pressure is 0. Okay, so and then we assume that the velocity is almost the same at point 1 and point 2. So we could take velocity is also equal to 0. And then we have the Z1 here. And then we have Z2. And then we have the losses. Okay, so and then for the term losses here can be rearranged, become losses is equal Z1 minus Z2. I think you could know we could bring the Z2 to the left hand side, so it will become Z1 and Z1 minus Z2. And according to our diagram here, so the difference between Z1 and Z2 here can be written as Y. So we could say that, okay, Z1 minus Z2 is equal to Y. So and then we could rearrange the calculation. So losses here can be calculated as tangent theta x is equal S naught over L. Okay, I think this is quite tricky, but I think you could understand. So tangent theta is equal to y over x. So we bring the x to the left hand side, so it's become tangent and x. So and then tangent theta can be simplified as S naught here, and the x here is equal to L. So the S naught is actually our assumption in the beginning of the calculation. Okay, so and then I think you already know this equation, so I'm not going to explain this in detail. So in fluid mechanics 1, we learned about major loss and minor loss. So for major loss, we could calculate the losses by using this equation. So we have F L over D V square over 2G, and the value of F here, actually it's if the flow is laminar, we could go for the equation F equals 64 over Reynolds number. But if the flow is turbulent, so we need to take a value of the F from Moody chart. So I think you already know how to take the value of F by calculating Reynolds numbers, and then you match with the type of pipe, whether it is smooth pipe, it is concrete, it is iron, and so on and so forth. And then you get the value of F in your Moody chart. So this is the basic calculation. So now we try to use this equation in our next discussion. So and then, okay, so if we do the same, so and then we could substitute this one. So we know that SL here, so is equal to HF, and then another equation for HF is equal FL over dV square over 2G. So and then we could embed all of these here. So and then if we equalize these two terms, so and then finally we could simplify it as this one. Okay, so and then okay, I'm sorry. So and then if we rearrange this equation, okay, after we substitute all of these, and then we rearrange this equation. So and then if you want to do this at home, so please, we have the diameter here, so we change into the hydraulic diameter. So we have the equation last time, so and then we could simplify it as this one. So in previous note we say that the 4 hydraulic radius is equal to diameter hydraulic. So we substitute with the diameter, that's why we could get an 8 here. So if you see, so we have 2 here, so 2 times by 4, so we could get the value of 8. So that is the one. So I hope you could do this at home, and then we could have this equation. So and then here, if we analyze this equation, we could find that the value of hydraulic radius here is actually to express the size of the conduit. So and then the value of S here is actually a parameter, the inclination of the conduit, that could affected the velocity. As you know, if the tangent is high, means the angle is bigger, so means the velocity will flow down in high velocity. So and then the value of 8G over F here, it is actually a constant, because the gravity is constant, and the value of F, as I said previously, it can be calculated by using Moody chart. So means that the value of G and the value of F is fixed. So when the value is fixed, so it is okay for us to say it is a constant. So means that the value of 8g over f square root here can be denoted as a c, mean a constant c. So and then we could simplify this equation, become v, the velocity, is equal to c rh s naught square root here. So mean rh s by the power of 1 over 2. So this we could have a simple equation of velocity. So and then if we want to calculate the flow rate, so we know that Q is equal A times V. So and then we add A here. So and then we add A at this equation. So we have this equation. So this equation is actually led by one French engineer called Chezy. So he used this equation actually to simulate and do the experiment about the Seine River in France in 1769. Okay, so and then the value of C here, as I said, it is the roughness. It is the behavior of the conduit, because if you see this equation, the C is actually consists of gravity and F, and the F here is actually comes from the roughness of the conduit. So means that the C here is the physical shape of the conduit. So means that it's different from one type to another type. So means that the value of C, it is actually a constant, and it needs to be determined one by one. So we call it as Chezy coefficient. So and then the Chezy coefficient is actually depends on the situation. So how to get the Chezy coefficient? I think in your fluid mechanics 1 you learn about the dimensionless and similarity. So normally people will do the experimental work, and then people start to compare the theoretical and then the simulation. The idea is simple. So let's say we know the hydraulic radius, because hydraulic radius is the dimension, mean the design of your conduit, and then we know the angle. Okay, means that we could setting an experiment by having this one. However, we do not know what is the value of C. So and then for our experiment, okay, let's say we could we calculate this first. We assume that the value of C is equal to 1. So and then we compare with this calculation, the value of from this calculation, we compare with the experimental work. So for sure it is not the same, because the value of C is not determined yet. So and then we could calculate the value of C depend or by comparing the real velocity of flow rate. Okay, I hope you could understand this, because this is I think already explained in fluid mechanics 1 previously. Okay, so this is the example. For example, we have a straight rectangular channel. So we have a rectangular channel like this. So let's say we have a conduit of rectangular shape. So the channel is 6 feet. Okay, so and then the water depth is 3. Okay, this is a 3 feet. So and then the slope is 2 degree. The friction factor is given as 0.022. So first we need to calculate what is the Chezy coefficient by using this equation, and then I hope you could remember this one. If the question given in British unit, so I think in fluid mechanics 1 we already discussed about unit. We have two type of unit. One is British unit and one is SI unit. So SI unit is what we learn, which is meter, centimeter and so on, but British unit is more about feet and mile. Okay, so and then if you use feet in your calculation, please make sure that the gravitational acceleration, the G, is 32.2. This is the official value of gravity in British unit. So for meter per second, it is okay for you to use 9.81 meter per second, but in British unit or conventional unit, you need to use 32.2 feet per second square. Okay, so and then we substitute the value of this one, and then we could have this value, and then we need to calculate the hydraulic radius. So this is the hydraulic radius calculation. So the cross-sectional area here is 6 times 3, so we have 18, and then the weighted parameter. Bear in mind that weighted parameter is actually the parameter that weighted by the fluid. So this is only the parameter that weighted by the fluid. So it is 3 plus 6 plus 3, so we have 12 here. So and then we got hydraulic radius is 1.5 feet. So and then tangent 2 degree, okay, we could calculate the tangent 2 degree from our calculator. So and then we substitute into the equation, we could have the flow rate, it is around 450 feet cube per second. So if the question is given in SI unit, so you could use this equation directly, but again, please make sure that you are using the correct value of gravity. So in meter per second, the gravity is equal to 9.81 meter per second. Okay, please remember this one. So and then here I will introduce you another type of equation that could solve the same problem. So we call this equation as Manning equation. So Chezy is the another researcher, and Manning is also a researcher's name. So it's proposed the same things. So and then I would like to bring you the idea of this one. So the inclination. So for example, we have a conduit incline at certain angle like this. So the inclination or the slope of the channel can be expressed in many ways. Okay, for example, this is the common expression that used in our in daily life or in the real application, even in our question. First, we will express in terms of degree. So for example, the slope is 2 degree and so on and so forth. So another one is it's expressed in terms of percentage. So 1%. So here for 1%, so means that it is 1 over 100. So it means that the vertical length here is 1 and the horizontal length here is 100. So and then, or it will write as fractions, for example 0.01 or 1 in 100. So I think I hope you could imagine the way people could express the slope. So bear in mind, because we are dealing with water flows, so means that it is weird if the slope is very big. Okay, normally people will use around 0.5, 1 or 2 degree angle. Because if you have, for example, you have a 30 degree, so actually you will create a very high velocity waterfall. So it will it is not good because it could exceed the safety limit of construction. So normally people will use a very slight angle. So please bear in mind, if you have if your answer shows a big number of angles, sometimes it is totally wrong. Okay, so I just shortcut the Manning equation because it actually do the same things like what Chezy do, but it use the SI version. So and then we could simplifies that the velocity for Manning equation can be written as this one. So and then please remember this equation, velocity is equal 1 over n times RH, hydraulic radius, by the power of 2 over 3, and S, the slope, by the power of 1 over 2. So V is the velocity, the unit is meter per second, and the value of N here is the channel surface roughness. So the RH is the hydraulic radius, and the S, the S here is the slope of the channel. So many equation, okay, it can be used for SI and British unit. So if we use British unit, the equation will different slightly like that. Okay, so if the SI unit, so it will become 1 over n, but for British unit you need to use 1.49 over n. Okay, so this is the difference between SI unit and English unit. Okay, so this is the value of n actually. As I said, it will be determined by using experimental work. So normally in our exam, I will give you the value of n. But if you work using these ideas, you need to determine the value of n by yourself. So normally the common conduit type can be found in textbook or any reference document of your conduit. Okay, so the example is something like this. So for example, if we have a smooth earth, so mean your conduit is actually the land. Okay, so maybe you could take it is equal to 0.018. So if your conduit, if your drainage is corrugated metal storm drain, for example here, so and then you need to take it is equal to 0.024. So if you see here, it is actually the range of the roughness is actually wide. It is not about the PVC and so on that we use in our pipe. So it's start from a drainage, the outside drainage that you could see beside the road, until the maximum one, for example, of the artificial river. So I will show you some question about the artificial river later on. So and then if you want to calculate the flow rate, so you just use the idea of Q is equal A times V. So we know the value of V here. So and then we multiply with the value of A, so you could get this equation. So and then normally we will calculate it at uniform flow. So means that the velocity distribution is almost the same at the bottom, at the middle, at the top of our open channel. So it also can be described as a normal discharge. So and then some people, they would like to use this equation in this arrangement. So it has AR 2 over 3 equal NQ over S square root. So why people sometimes in certain textbook they will write like this? Because this equation will show the idea of the idea of the open channel conduit. For example, the value of AR here, so as we know, A is the cross-sectional area and R is the hydraulic radius. So all of these, it is actually the design. So means it could show the channel geometry. So and then the N, the Q and the S, it is actually showing the flow properties, because the Q here is the flow rate, and then the flow rate will be affected by the value of N, means whether your drainage is smooth or not. So it will affect the flow rate. So at the same time, the slope. So if your slope is bigger, so means the flow rate will become higher. So that's why people want to know this, because later on in a tutorial I will show you, because sometimes people want to know what is the best design to fit the flow rate, or we have the design and what is the perfect the maximum or the safety flow rate for that design. So means that sometimes people are focusing on the flow and sometimes people are focusing on the design.